Since we're aware of quite a few specific standard distributions, you will be expected to apply the central limit theorem to all of the distributions you've encountered so far. So you should be able to apply it to the Poisson distribution, to the binomial distribution, to the geometric distribution, and to the negative binomial distribution. For each of these, as long as you can calculate mu and sigma, you should be able to go ahead and find the approximate distribution of the sample means, the approximate distribution of x bar. Okay, so let's try an example here. Be on the lookout for which distribution we should be using. So in this example, we're looking at a supermarket and the customers that visit the supermarket. The manager has observed that on average there are 20 new customers every minute. Now the 20 minutes there lets me know that I'm working with a rate because it was per 20 minutes. So I've spotted that we're working with the Poisson distribution. So I'm just going to start to state that. So x is the random variable that I'll use, or the notation for the random variable. And it follows a Poisson distribution where lambda is 20 per minute. So 20 customers arriving in the shop per minute. Part A asks us to find the probability that there's fewer than 15 customers in a given minute. So the time scale is the same. I can go ahead and just do this calculation straight into my calculator. I'll start with the probability statement. Probability that x is less than 15. That's the same as the probability that x is less than or equal to 14. And that's the number that I want to make sure I use in the calculator. So punch those buttons in and we get 0.1049. Okay, part B. Find the probability that in 1 hour, no more than 1,150 customers arrive. Okay, so we're going to need to scale that up to an hour. So I'm going to multiply by 60. 20 times 60, 1,200. So 1,200 customers per hour. And we've been asked to find the probability that no more than 1,150 customers arrive. So that's the same as saying less than or equal to 1,150 customers. So once again, this is ready just to punch into the calculator and we get an answer of 0.0758. Part C. Now here's where we've been asked to use the central limit theorem. We want to use it to estimate the probability that in 1 hour, no more than 1,150 customers arrive. So it's the same question, but can we use the central limit theorem? I'm going to start by considering 1 hour to be 60 1-minute intervals. So that gives me an n value of 60. I already know what the mean was because this was a Poisson distribution, the mean was 20, and I know that the variance was also going to be 20, which makes the standard deviation the square root of 20. So I should be able to define an x bar distribution. So x bar follows a normal distribution with a mean of 20, and this time round it's going to be a standard deviation of the root of 20 over 60. That cancels down quite nicely within the square root to just 1/3. So the standard deviation is the root of 1/3. Okay, well I know that I'm looking for a total time of 1,150, but for the x bar distribution, for the central limit theorem, I actually need to be working with an average. So the average time, if the total time was 1,150, is actually going to be 19.16 recurring. So I've got everything I need to be ready to make this calculation. So the probability I'm looking for is the probability that it's less than, that x bar is less than or equal to 19.16 recurring. And obviously I'm working with the x bar distribution. So this is the area that I'm looking for, expecting it to be less than 50%. Into the calculator with all the correct variables. I'm going to use an extremely small arbitrary lower limit. I'm going to use 19.1667 as my upper value, standard deviation as we discussed, and the mean of 20. Plug this all into the calculator, and that leads to an answer of 0.2820. So just be really mindful of this type of question. We weren't told an x bar value, we were told a total, and we had to use that to find our sample mean for ourselves. We weren't even told what the n value was going to be, but we had to just use some initiative that if we were going from an hour to a minute, an hour is 60 instances of a minute. So that gave us the n value equal to 60. So all the information was there, you just had to think a little bit creatively. You had to read between the lines. Okay, so that was the Poisson distribution. We're quite familiar with the Poisson distribution since we came across it quite early in year 12. Let's try and see if we can apply the central limit theorem to one of our newer distributions, to something that we've come across in year 13. As we read through, just see if you can tell which distribution we're referring to. So Billy is the football team captain. Every week he calls around trying to make sure he can gather enough of his friends to have a squad to play. The probability that each individual friend agrees to play is 2/3, and he needs to get 10 other players to make a full squad, which is 11 players including himself. So, what distribution are we working with? Well, we're looking for 10 successes. The probability of success is consistently 2/3, and we can assume that each of his friends respond independently to each other. So this sounds very much like the negative binomial distribution to me. So we can just define that here, and we can use that to respond to the questions. So firstly, we've been asked to calculate the number of friends we would expect Billy to have to call to find 10 other players. Really just been asked for the expectation. The expectation of a negative binomial distribution is R over P, the number of successes that we want divided by the probability. So in this case, that's 10 over 2/3, and rearranging, simplifying, punching into your calculator, any which way, we get 15. I'm just going to do the variance here as well, just out of habit. I'll always want the expectation and the variance worked out together. So RQ over P squared, and working that through, we get 15 over 2, or 7.5. So I've got my expectation and my variance, likely to come in handy later on. Part B of the question, find the probability that Billy has to call exactly 12 friends. The probability that we need 12 trials to get the 10 successes. Well, we're going to use our probability function as we usually would. We know that the last trial will definitely be a success because that would be our call to stop calling round to more friends. And we know that out of the first 11, we needed 9 successes. So the binomial probability function for 9 successes from 11 trials, and then we're going to multiply that by 1 additional success. Rewriting, we get it into that negative binomial form, and then obviously just punching this into the calculator gets us an answer of 0.1060. Okay, part C says in a season, Billy's team plays 25 matches, so that's going to give us n equals 25, and we're asked to estimate the probability that the mean number of calls per match that Billy has to make will be less than 15.5. So we're going to go ahead and state the X bar distribution. The mean, the expectation, we'd already calculated up above, that was 15. The variance, it seems I was smart to calculate it early, was 7.5. So here we're going to write out the standard deviation is root 7.5 over 25. And that's what we're going to use in our calculation. Okay, so a quick diagram. In this case, the mean was 15, as we said, and I'm actually looking for the probability that X bar is less than 15.5. So we can see on the diagram, that's a large proportion. It's going to be more than 50%. This is where I'm so happy that we got this diagram and why it's so useful. So I'm expecting a value bigger than 50%. Outside of this, a large value like that might have thrown me off because we usually end up with small percentages, especially when we move to hypothesis testing. But here I know to expect a large value. Okay, so let's just get our calculators ready, put in an arbitrary small value, upper limit of 15.5, standard deviation, and the mean, and that all leads to an answer of 0.8193. So once again, I was expecting that large value. I'm happy that I've done my calculations correctly in this case. So once again, here we're trying to apply the central limit theorem to the distributions that we were aware of before. These questions, as you come up across them in assessments, would usually get you to work on that distribution natively, as in questions just on the Poisson, questions just on the negative binomial, and at the end, let's see if you can stretch that further and apply the central limit theorem.